Hey everybody, it's Jay Henry. In this video, I want to actually implement the machine learning model architecture that will allow us to train our model to recognize different stages of plant maturity. Going to base this model architecture off of Resnet, which was, I think, introduced in 2015. And as far as I know, it introduced the concept of a residual block. A residual block is you save the output of a previous block, and then you add it into the output of your current block. And what this does is it helps prevent the problem of vanishing gradients in very deep architectures. And so I'm going to code up a implementation of that model and talk at a very high level about the different steps and the ways that that is accomplished without going too deep into the mathematics of it. So as a refresher, we've got our training data that we used these video files to produce individual image files for different plants that are in different stages of growth. And these are the images that we're actually going to feed into this model to using the data generators to actually train the model. And I think you'll see why these data generators are so handy as we go through this, because we're not actually going to have to code up how we set our labels for the classes. And usually you'd create a set of one-hot labels that tell your output what class they are, but it's actually going to take care of that for us. So I think without further ado, create a folder here for Resnet in case we want to create different architectures to solve the problem in different ways. And I'll just add a single Resnet. I think what I'm going to code up is a Resnet 50, meaning it has 50 layers. It may end up different than that, and we'll kind of see when we do the model summary at the end, but I'm going to call it a Resnet 50. And what we'll need to do here is import, we're using Keras as our framework, so we need to import some stuff from Keras, some helpers. Let's see, sequential, probably need model, from, and actually, that should be from. Okay, it's hard to talk in program. Layers, import, and these are the different layers that I think we're going to use. And I'll talk about each one again at a high level as we use them. And try to give you an intuition of why we chose them. Activation, batch normalization, flatten. So it's got two T's, good. Dense, add 0 padding, 2D. Okay, I think that's it. And then we're gonna also grab an initializer. And initializers, we're gonna import. I'm not real sure how to pronounce this, but basically what this initializer does is you give it a seed and it gives you a pseudo-random normal distribution of data, which you think it can then use as the starting point for a kernel. I'll talk a little bit about what kernels are. They're actually a pretty simple concept, I think, once you understand them. They're basically, you're going to take a matrix of numbers, and a kernel is a different matrix of numbers that you're going to multiply them by to get a third matrix, which is your feature representation. And so you want to kind of randomly initialize those kernel matrices so that you can learn different features. I don't think there's much more to it than that. So as I build out this model, there's going to be a lot of redundant block declarations, and they're going to do some very similar things. So I think the first thing I want to do is create some helper functions that will initialize these blocks for us. Let's do proper spacing. Filters, stage, block. And this is, like I said, it's going to be our base block. This is going to be operations that are common for most of the blocks that we're defining. So we'll use this helper function to build out more complex blocks without rewriting a bunch of code over and over again. Name base. So the first thing we're going to do is give it some name format strings so that we can give things different names based on what kind of block it is and where we are. And this is going to be really useful when we look at the model summary later. We'll be able to tell, each one will have a name, and we'll be able to tell kind of from the summary the structure of the model. Batch norm base name. Let's see, let's say batch norm doesn't have to be human readable necessarily. And then we'll do stage block. I like this this Python kind of string interpolation syntax. Let's see, F1, F2, F3. We're going to be passing in arrays of features, which is just going to be arrays of 3 different numbers, but it's going to be the how many features we want to get out of each block. And so these are going to be passed in as filters. And then we'll start building the model. And then we're going to go com2d. So com2d is a convolutional layer. If you're semi-familiar with convolutional layers, think of your image as a like a checkerboard, right? And a convolutional layer is going to take a subset of squares on that image and consider them independently so that it can build out features. And this kind of goes back to what I was saying with kernels. It's going to take, let's say it's going to take a 2x2 block of pixels. Normally you wouldn't do it that size, but a 2x2 block of pixels, and then it's going to multiply those values by a kernel, which would be, a 2x2 kernel, and then you'll get a different output, and that's how it'll learn the features. So we're going to have a lot of these in this model, but just think of it as a sliding window over your entire image that considers individual regions independently. Let's see. Kernel size. A lot of these parameter values are chosen to make the math work. And I'm going to show you that the kernel sizes will change when we change between different numbers of filters, because we're basically resizing the image at that point. Let's do strides. Strides are how fast it moves around the image. Do valid padding. We'll do name, and this is, we're going to do, I think, is that right now? 2A, yeah, format, and then we'll feed in the base name. Company base, so that's just kind of a handy shortcut. And then the kernel initializer is the, again, we're going to give it a semi-random normal distribution of data. I think that's it. Yep. And then we'll create batch normalization layer. And batch normalization, so in matrix multiplication and machine learning, it's very helpful to have your data normalized within a range, and there's a lot of research out there about it. I think the optimal values are like between -1 and 1, but basically you want to take all your data and use the standard deviation and the mean and all that, and normalize it within a range so that it's easier to work with. So that's what these layers are for. I'll go to A, and then format, and this is the BN batch norm base name. Yeah, and then we'll do that. And we'll pass X in here. And so when I'm passing X at the end of all of these, basically what we're doing is building up layers and passing the output of each previous layer into the next layer. And so that's why X keeps getting redeclared and passed in. It's getting matriculated through the model. And then activation, rectilinear units is, you know, kind of the industry. I don't know if it's industry standard. It's what I always use. So activation is whether you're going to get a signal out of an individual neuron or not, whether you're going to trigger it to fire. And I think you could, initially it was like square waves, so it was either on or off, and then it became sigmoids, so that, you know, it had an S shape, and that worked great because it was more differentiated than a square wave, but you could get saturation both at very low values and very high values. And so what a ReLU or rectilinear unit does is it basically replaces negative values with 0, and then anything non-zero is just whatever that value is. And so it almost looks like a flat line, and then it raises in a linear fashion. Okay, and that's that. And this should be A, not B. And so now I'm going to take a shortcut. We're going to want another one of these. We're actually going to want 2 of them, sort of. We're going to leave the activation off of the last one. And so I should be able to just replace the names and obviously the filters. F3, C, and this will just keep it, you know, keep it nice and straight when we look at our summary of where we are. You know, we're going to be in 2B, 2C, 2A, and then we'll have our stage and our block represented in there as well. And that's it. We're going to return that, and now we're going to build on top of that. So for our model, we're going to have 2 building blocks that are almost exactly the same. And the first one I'm going to build is the identity block. Stage block. And this is where I'll introduce the residual block. So X residual. And I'm just going to assign that to X. And then I'm going to reassign X equals base block. I'm going to go XF filters stage block. And then we're going to add these together. And so this is this concept of adding the output from previous layers back in to the output from the current layer. And this, you know, if we have any kind of layer that causes the output to skew in some direction wildly, that, you know, will get magnified as we go along the model, adding in the output from the previous model kind of gives it a memory and keeps it from getting too skewed in one direction or another. Most of the research I've done on it says that it was done to solve the vanishing gradient problem, but I think it also solves the exploding gradient problem. If anybody knows, you know, a final answer to that, please leave it in the comments and let me know. And then we're going to activation. And so you noticed in the base block we left activation off of the last block in here, and so we're actually going to do that here after we've added the residual back in. I think that's good. And let's see. Okay, so that's an identity block. Now we're going to define something that is almost exactly the same. I call it a convolutional block, and it has the same parameters, and it actually does almost exactly the same thing, except, and then I'm going to change the stride here. The difference that you'll see here, and I actually need to copy these in, and you'll see why in just a second. The difference between this block and the identity block is this one's actually going to do a convolution over the residual to change its size so that the math works out. And you'll see how we use it later on. But this is, I think these are going to work the way that they are. Yep. And so I got to create my residual. Residual equals X. We're going to do, again, a base block. X equals base block, XF filters, stage block. We need to use F3. We need to use the third filter to resize it so that the math works out. And then we're going to actually, and here's where we change things a little bit. We're going to convolve over the residual block and reshape it. Equals F3 kernel size 1 and then strides. Gonna change the stride. I think that's probably fine. Set our padding. Give it a name. I'm gonna say dot format conf name base. I think that's good. We're going to use the same kernel initializer. Kernel initializer equals uniform and c equals 0. And then we're going to pass the x residual into this. And then we're going to do batch normalization on this. And so it should kind of make sense that we have to do the same steps in here that we do to the output of other layers to make the math work. A discussion on linear algebra and matrix multiplication is way beyond the scope of this video, but if you're familiar with it, it'll make sense why we do that. And then we'll pass in the x residual. And then we're going to add them together just like we did in the identity block. I'm going to go add, and this is where they need to be the same shape. X residual, and then we're going to activate. And then we will return x. And I think that is all correct. If we have any bugs in there, I'm sure we'll find them as soon as we try to run this. So now that we've got those kind of building blocks put together, let's no, yeah, because it's models. Let's actually build out the architecture, the high-level architecture. So we're going to create model. Input shape and classes, and we're going to create an input layer. X input equals input shape, and then we're going to zero pad it. And zero padding is exactly what it sounds like. It basically adds columns and rows of zeros around your image pixels, and it does this to make the math work, to make the matrix the right size for multiplication and addition. All right, so we're going to do an initial convolution over this image. 2D. We're going to say 64. I'm sorry. Yeah, that's right. Do 7 by 7. Do strides 2 by 2. Name 1 1. Kernel initializer should look. Do I have everything right there? I think so. Equals uniform. C equals 0. Pass in the output from the previous layer. Let's do a batch normalization. Let's say axis equals 3. Name equals, doesn't really matter, but we'll just call it being conv1. I think that's fine. And then let's do an activation. Did I get it? Oh, so close. And then max pooling. And max pooling is a that's not going to work. Max pooling. Max pooling is a downsampling technique where it basically takes in this case we're passing in 3x3, so it'll take a 3x3 snapshot of the image pixels, and it will take the maximum value and output that to the stride equals, output that to the layer output. So the resolution of the image will go down, but the highest value in the area that was scanned will be preserved. It's uppercase X, not a lowercase. And now we can start using our building blocks. And so we're going to say 64, 64, 256. So we're going to pass in 3 different filters, and then each level is going to output that number of filters based on the base block we've got down below. And now you'll see how we can use the building blocks that we created. Let's see, filters equals filters, stage equals 2, block equals A. Now our names will make a little bit more sense, because, well, when we do the summary, you'll see that when we go stage 2, 3, 4, 5, and we start out at block A, that we will, be able to make sense of the structure that we have. Now we're going to add in identity block. Identity, come on, block. X, 3 filters, stage equals 2, block equals B, and so this is going to preserve information about where we are in a human readable-ish format. We'll go, this will be C, and that's it for this layer. So now I'm going to take a bit of a shortcut, and I'm going to create the next couple just using copy and paste because it's faster. And this one, it's actually going to be 128, 128, 512. Stage is going to be 3 here. Filters are going to be the same. I think that's good. Let's add another one in here. Yeah, let's make it a little bit deeper. And then we'll just, again, copy this, create another one. I like to keep my spacing the same where I can. Alright, 256, 256. Let's do 1024. We're going to be on stage 4. And then let's add 2 more of these. I think 2 more. Let's do E and F. That should be good. And I'm going to copy this. We'll do this one more time. And do, what do we start with here? 512, 512, 512, 10, and 2048. I think is the pattern. And this is stage 5. And let's make sure these all match up. And I think that's it. And so now we've got the main structure that we want, and you can see this is, in and of itself, this is a pretty deep model, but when you figure in all these additional models down here, it's going to be a very deep model. Why am I getting X here? There's no return X, return X. Well, that'll be good to do. All right. So now we're going to do a different kind of pooling, and we're going to use average pooling. So average pooling is very much like max pooling, except that rather than taking the maximum value in your area, you take the average of the values. It's pretty simple. And then we're going to flatten this out, and so this is actually going to take these each of these matrices and flatten them out into a vector so that we can connect them all to a fully connected layer and then get some kind of output from them. So we'll say flatten X, and then we're going to do a fully connected layer. Classes activation equals softmax, and softmax is basically going to give us, if you've got 10 outputs and they're all equally likely, you're going to get a 0.1 prediction for each of them, because the outputs for all of them have to add up to 1. If you have one that is 90% more likely to be the prediction, it's going to have a 0.9, and all the other ones might have like a 0.01 or something. But the idea is you're going to get out a vector that has values for each of the classes it's trying to predict, and the total of those predictions will add up to 1. I think it's not any more complicated than that. We're going to name this fully connected. We could name it output too, but it's fine. Kernel initializer, again, Glorot. I love that name. Equals 0. You can change the seed here if you want. I don't think it would affect anything. Just give you a different pseudo-random generation. And that's it. And that's all we're going to do. Now we're going to create the model. We'll do that. We'll say inputs equals x input. We'll say outputs equals x, right? And then our name will be Resnet. And again, I'm not sure this is actually going to be 50 layers. It may be more than that, but whatever, that's what I'm calling it. We're going to compile the model. Optimizer. Atom. So the optimizer, Atom is adaptive something or other, but basically think of it as stochastic gradient descent with some additional features. So Atom will give you momentum when you're doing your gradient descent, so it helps you not get stuck in local minima. So if the gradient is changing rapidly, I think that the momentum of the change of the gradient gets added into the gradient descent learning rate. And so think of it like a marble rolling around on a gradient. If it's going down really fast and it hits a local minima, it might have enough momentum to roll up over and get a little bit deeper. But again, it's just gradient descent with some additional features. We'll do loss, cross entropy, and metrics accuracy. I think that's it. Return model. Alright, so now we've defined a Resnet computer vision model, which is going to be very deep, and it's going to have, let's see, 0 padding? Probably 0 padding 2D, right? Is going to have a lot of filters that it spits out, so it should be able to learn a lot of different things about our images and make some good predictions. But let's find out. And so I think I'm going to go up to, just to make things easy, I'm going to go up to the root of my project and create a new file here to train this. So let's say train plant maturity model.py. Yeah, why not? Import OS. I need this so that I can use PLAD-ML because I've got AMD GPUs and I don't want to do it over on CPU. In Byron, and we're going to set the Keras backend. PLAD-ML dot Keras dot backend. I think that's right. All right, and then import generators. Now remember, we have our model data generator. And so this, like I was saying before, like we're not going to have to set up our, we're not going to have to manually read in our images and convert them to matrices of numbers, and we're not going to have to set up our labels of one-hots to tell it what class it is. The model data generator is going to take care of all of that. And then let's import our model definitions. Resnet.resnet50 as Resnet, I think. And then we'll declare some hyperparameters. One of them is batch size. How many images do we want to process at a time? Target height 64, target width. These are very low resolution, so it'll be faster. If you want much higher resolution, which should improve accuracy, but it'll be slower, you know, you could change that. How many steps in each epoch? That was bad. How many epochs do we want? Normally it would be more than 5. I'd do probably 10 and 1,000 steps per epoch, but I think this will give us what we want for this. And then how many validation steps do we want to take? And I'll just do 10. And now we can train the model. So we'll say model equals resnet.create model. Create model. Our input shape is going to be target height, target width. If you're using a non-square image type, then you might want to just make sure that those are in the right order. And then 3 is for the number of channels. RGB, we're passing in color images. This is equals 2 because we really only have 2 classes worth of data here. So. And then we're going to show the summary, and this is what I was talking about. You'll see the output here when we run this. It'll actually show us what the shape of the model is and what each layer looks like. That's kind of cool. It's a good sanity check. And then we're going to get our generators, both a training generator and a validation generator, which are slightly different. Create generators and give it the batch size, and then we're going to want to stick this somewhere. And there's the output of this. There's actually going to be 2. Well, I'm just telling it where to read in from right now, so we'll get into that in a second. Maturity. That's where we're going to get the training images, and then we'll tell it where to get the validation images, which are separate and not included in the training set at all, so that we can see how well the model was able to generalize. And then again, target height, target width. Again, if you're using non-square images, just make sure those are in the right order. Can't remember off the top of my head. And then we're going to fit the generator. And model fit generator, so we're going to give it the train gen. We're going to give it the steps per epoch, and that's cleverly named epoch steps. We're going to tell it how many epochs we want. I should name that epochs. That doesn't make sense as epoch to be plural. Validation data is going to be our valgen, and then validation steps, and that is, so that'll do all the training. That's all we have to do to tell it to use those images to train. And I'll show you what the output looks like. But then when it's done, we're going to want to save the output so that we can quickly load it up and use it to make predictions. So the model actually has some built-in functionality to create a JSON file for the structure. And why is it telling me that model doesn't understand? Well, it's not giving me autocomplete on that, which worries me a little bit. We'll see. Now we're going to have to save both the format of the model and the structure, and as well as the trained weights, and we'll save those in 2 different files. And so we'll do models. I think we have a folder for trained, and then format, and then plant maturity dot JSON. We want this to write, and then we'll say as format file, and then we'll just write it. Format file dot write, and model format. Okay, and that's, let me just verify that we have the right structure here. Trained format weights, great. So that should save it. Model.save weights, and this is going to save a binary file, and so we'll just save it to the weights directory. Trained weights, models trained weights, plant maturity dot, it's an H5 for extension, and that's it. That's all there is. And we will go ahead and save this, and then what is this? That's wrong. Maybe that's why it wasn't giving me autocomplete. We'll go ahead and save this and see what the output looks like. Alright, so let's open up a new terminal. We're at the root here, so we should be able to just train plant maturity model.py. Let's see, it's trying to open up my GPU, which is great. And then this is our model summary, and so as you can tell, it's quite deep, and it looks like it is more than 50 layers. It looks like it's quite a bit more. But yeah, so you can see why we gave it names, and you know, you can see how the different shapes of the matrices change, and the operations that are taking place on each one, and so this is a healthy summary, and a helpful summary that gives us information about what our model looks like. And so this is going to take some time to train. I think I'll probably pause here, and then when it's getting close to completion, we'll start back up, and I'll show you what it looks like as it's going through the epics and training and validating. So hang on just a second. Okay, it looks like our model is done training. I'll kind of walk you through what we're seeing here. So each of these represents the steps within the epics. You can see epic 2 of 5, 500 of 500 steps complete. It gives you estimates for how long it's going to take, but these are the numbers that we really care about: the loss, the accuracy, and the validation loss and validation accuracy. And what these numbers mean is that while it was training, the average accuracy was 98%, 99%, 99%, 100%, you know, close to it. And then a validation accuracy, these are 100%, means everything that it validated, it, you know, got exactly right. I'm actually happy that the validation accuracy down here was a little bit lower. Whenever I see something like this, I almost don't believe it. But this, you know, this looks like a valid result. So I think in the next video, what I'm going to do is take, and this should have saved. Yeah, so it saved the trained weights, which I misspelled. That's awesome. What did I do here? What did I do here? Yeah. I might rerun it just to make the name right, but it saved the weights, which is binary file, and it saved the format of the model, which you can see is massive. I'm gonna go ahead and let's see if I think I'm gonna check these in, because I'm gonna change them. So let's do git add all, and it's gonna take a second because that weight file, that H5 file, is actually pretty large. Commit am trained Resnet model for plant maturity and saved weight and format files. We'll push these up, and I'll put the URL for the repo in the description. Feel free to check it out. Feel free, you know, if you think it's good, feel free to actually use this model. All you should have to do is change the training data and it should be able to recognize just about any type of image data. But if you found any of this helpful, please like and subscribe down below, so that you can get updates on the next step. And in the next video, we will create a service layer that loads up the weights and makes predictions based on images that are passed to it, and then we'll actually pass some new images to it and see how well it can predict the plant maturity. If I got anything wrong here, or if you think there's a better way to do it, please mention it in the comments so that I can learn from it. But until next time, thank you for watching. Later.